last lecture we have completed how to calculate the depth of one-way continuous slab. So now today we are moving forward and we will see uh, how to calculate the load. This is the loading calculation. Okay. So now load calculation is we need to do the same thing in the load calculation also. We have to
सर आवाज कट होतोय.
आता येतोय का? आता येतोय का
क्लिअर आहे
आवाज?
सर. हो
क्लिअर नाही का आता?
हा हा सर यायलाय.
यायला लागलाय का आता? यायला लागलाय
हो
का
सर
नाही? क्लिअर आहे ना?
येत हो क्लिअर आहे.
हा थोडं मध्ये आधी नेटवर्क प्रॉब्लेम येत असेल मे बी. So now load calculation here. So load calculation we need to do. So dead load of the slab. So first of all, we will calculate the dead load of the slab, which is similar to that of our one-way slab. So we take the depth of the slab 0.115 into 25. So the dead load comes out to be 2.875 kilonewton per meter square. Now after that, we need to calculate the floor finish. Floor finish is 1 kilonewton per meter square. It is assumed because anything regarding the floor is not given in the numerical. So we have assumed this value. After that, now total dead load. So the total dead load is calculated. So that total dead load means the addition of these two sulfate plus this 1 kilonewton per meter square. So it is now 3 kilonewton per 3.875 kilonewton per meter square. So the factor dead load. So multiply this value by 1.5, you will get the factor dead load, and its value is 5.81 kilonewton per meter square. The value. Now this is the all calculation is about the dead load. So this all calculation is about the dead load. So after that we need to calculate the live load. So live load it is 3 kilonewton per meter square. Okay, as many times the live load is already given in the problem, so you have to see what is the live load is given. If the live load is not given, then their type of the building may be given to you. For which type of building you need to design the slab, that may be given to you. So that I have already told you for residential building what is the live load, for commercial building what is the live load while designing the slab. So accordingly now live load is 3 kilonewton per meter square. So factored live load, so WUL, multiply this live load by 1.5, then we get the value 4.5. This is 4.5 kilonewton per meter square. So assuming 1 meter wide strip, this we have assumed in the one-way slab also. We always assume the width of the slab as 1 meter. So assuming 1 meter wide strip of the slab. So whatever may be the width, we are not considering that width over entire width over here. We just assume that the width of our slab is 1 meter, and we are going to repeat the same design for 1 meter interval. So after the loading calculation now, we will come to the bending moment. So bending moment calculation. So for the bending moment calculation, we need to go for the clause number 22.5.1. This is very important clause, 22.5.1, table number 12, page number 36, I think. Okay. So this bending moment is calculated now. Here you can see that the bending moment for end span is calculated. Also the bending moment for intermediate span is also calculated. As our slab is the continuous slab, you know that. So it is supported at the end by the walls. If you see the problem carefully, it is supported at the end by the walls, and intermediate beams are provided. And now the bending moment at end span. So whatever our end span is there, if we go to the previous slide for the end span, then the end span will be the last span which is given over there. So the bending moment is calculated at the middle of the end span. See this. At the middle of the end span, the bending moment is calculated, and after that, at support, okay, at support, which is next to the end support, the bending moment is also calculated over here. So if I show you at the middle and at the support next to end support in the diagram, then we have to go back. You will see the slide. I will tell you where exactly the bending moment is calculated. Now see here, here now over here. See, this is the end span. This span is nothing but this is your end span. These two spans are your end span, and the remaining these three spans are the intermediate span. This is your intermediate span number one. This is your intermediate span number two, and this is your intermediate span number three. So now for this, see this is the intermediate span. So bending moment calculated at the center. Okay, so here this is the center point. Bending moment is calculated at the center, and also for the end span. So here also bending moment is calculated at the center. These two moments will be same as the span is same, and after that the bending moment is calculated at the support. Now see, this is the end span. This total is the end span. So it is having four supports, one, two, three, and four corners. It is having four corners. So bending moment is calculated at the support next to end support. So this is the support which is situated at the end. Now if you see that this is here, whatever may be the support which is over here, this is called as end support. This is called as end support. Okay. Here also, this support is nothing but it is end support. Okay. And the support which is next to end support. So this is the support which is next to the end support. So if I draw the line diagram of these two clear, suppose this is our discontinuous slab. This is end support. This support which is at the end. These two are the end support. And in between, how many supports are there? 1, 2, 3, and 4. So here I need to show the intermediate 4 supports. So I will show those supports over here. See here, support number 1, then 2, and then 3, and this is 4th support. हे मधले जे 4 सपोर्ट दाखवलेत मी ब्लू याच्याने, ते सपोर्ट कुठले आहेत तर आय विल शो ओव्हर हियर. दिस इज फर्स्ट support, intermediate support first, this is intermediate support second, this is intermediate support third, and this is intermediate support fourth, and these two supports are the end support. So whatever I have given numbering in the blue, you can say in the blue ink, that supports I have shown over here, these are called as the intermediate supports, and whatever I have given the name in red color over here and the supports I have shown in the red color, that is nothing but your end support. Now what they have told us, so they have calculated the bending moment for end span. Okay, now the bending moment is calculated for end span. First it is calculated at the center of end span. So here, this is the center of end span. This point is the center of the end span. And after that, it is calculated at the support which is next to end support. Now here see, you can see this is our end span. So this support is our end support. This support is nothing but our end support, and moment is calculated next to end support. Next to end support is this point. Here the bending moment is calculated. Similarly for this span also, this is your end support, and the bending moment is calculated next to end support. So here at this point, the bending moment is calculated. Okay. So I hope I cleared with the things where the bending moment we are exactly going to calculate. And if you see the profile of the bending moment diagram, then it will be something of this sort. Here the sagging will be there from this point to this point. Again the some bending moment will be there at this point. This is the diagram. Again for this span, it is again sagging bending moment. Again hogging bending moment at the support. Again it will sag. Again here somewhere hogging bending moment. Again for this span, sagging, hogging, then again sagging, and it will come to 0. Okay, so this is the bending moment profile. If you see, this is your positive bending moment sagging, This is also positive bending moment. Here it is also positive. This is also positive. This is also positive. And all the hogging bending moments are negative bending moments. And you notice that you are getting the hogging bending moment at the support only. Here where we are provided the support, at the support the hogging bending moment is there. So what we have done basically for this end span, now if you see this end span, what we have done over here basically, we have calculated the what is the sagging bending moment, that is what is the positive bending moment at the center or at the mid span, and what is the negative bending moment, next to the end support. Okay, next to the end support, here we have calculated. So now coming back to our calculation, I will clear all these drawings. Do you have you noted all these things? So I will now clear the drawing. You do simultaneously also notes taking with me, so it will be very helpful to you. So now coming back to this point, here what they have said, at the here they said that bending moment for the end span at the middle of end span. So at the middle of end span, I have already told you, at the middle of end span means the bending moment is calculated, that is the sagging bending moment. So the coefficient factor for that is 1 by 12 and 1 by 10. WL square is the common term. Now if you see over here, so this is this WL square. This WL square is the common term. We need to multiply the coefficient by WL square. Once dead load, we have to take dead load. Once we have to take the live load. And the coefficient factors are 1 by 12 and 1 by 10. And those are come from this here. This clause number 22.5.1, table number 12, page number 36. Now we will go to the IS code, page number 36. So you will understand it clearly from where those factors are coming up. You just see this formula only now. For a time being, you just see this formula. It is WD L square by 12. WD means dead load, and it is WL L square by 12. Okay. So here at the support also, so at support next to end support, WDL square by 12, again minus, here you will see the minus sign. The sign is here negative because the bending moment is hogging moment, so negative sign will be there. WL square by 10, that is 1 by 10 is the factor here, and 1 by 9 is the factor over here. Now we will move to the IS code to tell you exactly. So I will stop my screen sharing here, and we will go to the IS code now. Now what the IS code says, let us see. The page number, what was our page number? I think page number 36. So page number 36, somewhere here, this is 27, way behind. Page number, table number 12. We need to look out the table number 12. We will read that table, what is given in that table, so it will be easy for you to understand how that coefficients come and how it is taken into the consideration. Now this is page number 36 and this is table number 12. Okay. Now if you see over here, this is the page number 36 and table number 12. Okay. So what this table says, bending moment coefficients. Okay, these are the bending moment coefficients for continuous slab. So we have to take into the consideration. So here you can see the type of load. So in the type of load, there are two types of loads are given. First is this one, dead load, and second is imposed load. Imposed load is nothing but imposed load is called as live. Imposed load is nothing but it is live load. Okay, now you focus here. So under the types of load, two types of loads are given. First is the dead load, okay, and second is the imposed load. So now we will move to the next point. here. Now the coefficients are given over here. So see, near the middle of end span. Okay, so first it talks about the end span. Okay, end span. End span च्या middle ला. Middle of the end span means I can call this as the at the center of the end span. At the center of the end span, what is coefficient? It is 1 by 12. Okay, it is 1 by 12. 1 by 12 for what? For dead load. So this is 1 by 12 for dead load, and it is 1 by 10. 1 by 10 for what? Live load. So and it is plus. So the coefficient is plus 1 by 12 for dead load and plus 1 by 10 for live load. And here the note is given: for obtaining the bending moment, the coefficient shall be multiplied by total design load and effective span. Okay, so total design load W into L is total design load and effective span is L. So it will be, see, our total design load will be W into L. This is our total design load because we have calculated W in kilonewton per meter. If you multiplied it by length, then you will get the total design load, which unit is in kilonewton, and then the effective span. Effective span is again L. Effective span is again L. And if you take the product of these, then what you will get, it is WL square. WL square. So this is the coefficient by which, this is the value to which we need to multiply by these coefficients. Now if you now you see very carefully. So near the middle of the end span, for dead load the coefficient is plus 1 by 12. For live load the coefficient is plus 1 by 10. Okay, and now we will see here at support now for end span again. So this is end span, so here it is again end support or end span. So what they have given, at support next to the end support, what is the dead load coefficient? So this is the dead load coefficient, it is minus 1 by 10. And at support next to end support, what is the live load coefficient? So this is the live load coefficient, it is minus 1 by 9. Okay, so remember 1 by 12, 1 by 10, it is at the middle of the end span, and at the support next to the end support, it is minus 1 by 10 and minus 1 by 9. Okay, so now again we will move to here our slide. So again we will move to our slide over here. So now we see here again. Now we will see how it is taken into the consideration. So now bending moment at end span that to middle. I have already told you WL square is the common multiplying term. Okay. Now when you take for dead load what was the coefficient? 1 by 12. So here I will write for this. So 1 by 12 is the coefficient for dead load, and I need to multiply this by WUD into L square. This is my first bracket. That is what is written over here. That is what is written over here. Okay. Now this is the coefficient for dead load. Similarly, you have to take the coefficient for live load. Now if I go for the live load, then for live load, see here, for live load, it is 1 by 10 is the coefficient and WL square is again common term. So we have to add this. So plus, I can write over here plus, here in the bracket, 1 by 10 because the coefficient is positive, and WUL live load into L square. This is the span. This is whatever is written over here, which I am indicating by blue. This is the live load coefficient by blue. This is for the live load. Okay. And whatever I have indicated by red, this is for dead load. So this is the dead load coefficient. I hope you understood. Is it clear? Please give me the reply. So we will move further. Yes or no? So I hope you understood this. So now moving further, at support next to end support. Okay. So we need to calculate the bending moment at next to the end support. At support which is next to end support. I already told you for dead load the coefficient is minus 1 by 10, which is written over here. So dead load the coefficient is minus 1 upon 10, and this is dead load into L square. WL square is the common term over here. We have to multiply by W dead load into span square. Minus for live load, again the coefficient is minus 1 by 9. So this is 1 by 9. Minus 1 by 9 is the coefficient for live load. Live load into L square. Okay. So now just if you put the values over here in this formula, so the values are put. So here WD, what was our dead load? So here we have calculated the dead load. This is the value of dead load. This is our ultimate dead load. And what is the value of live load? Here we have calculated the ultimate live load. This is the value of our live load. So the dead load is 5.81 into L square. L is 3 meter. Span is already known to us. In the problem itself, give the span is specified to us. So it is 3 meter divided by 12. Okay, the coefficient is 1 by 12. So divided by 12 plus 1 by 10 is coefficient. So 1 by 10 as it is into live load. What is live load? Live load is 4.5. This is the live load 4.5. So 4.5 into L square. WL square again into term. If you simplify this, you will get the answer as 8.407. This is the answer. 8.407 kilonewton meter. Similarly now, here at the support which is next to end support, again we can calculate the bending moment by keeping the values over here. So again minus 1 by 10 as it is. So this is minus 1 by 10 as it is WL square. So this minus 1 by 10 is the coefficient for dead load. So here we should take the dead load in place of W. So our dead load is 5.81. So that dead load is considered over here 5.81 into this L square, okay, span square, minus again it is 1 by 9 is the coefficient for live load minus 1 by 9. So here it is minus 1 by 9 divided by 9. Live load, the value of live load is 4.5. That value is kept over here 4.5 into L square. So if you solve this, you will get the value as minus 9.729. So up till now we have got these two bending moments for end span. Now this is the calculation for end span. This calculation we have done, it is for end span. I will put bracket over here. This is done for the end span. Now we will go for intermediate span. Now we have to see the calculation of intermediate span. So again for the intermediate span, what they have mentioned, the bending moment for intermediate span means other than end spans. I have already told you the spans which are at the ends are called as end spans, and except those end spans, we are having three more spans which are intermediate span. So the bending moment is calculated at the middle of interior span and at the interior support. Okay, interior support is nothing but intermediate support. So at the middle of interior span, the coefficient is 1 by 16 for dead load and 1 by 12 for live load. And at the interior support, the coefficient is minus 1 by 12 for dead load and minus 1 by 9 for live load. So again, we will go to the IS code. You see these coefficients now. For interior span at the center, it is 1 by 16, 1 by 12, dead load and live load. Okay. And at the interior support, so intermediate support, it is minus 1 by 12 and minus 1 by 9. So we will move to the IS code again. So I will clear all these drawings. So in the IS code on page number, same page number. So again, we see the IS code. So here the IS code. Now this is the IS code. So here if you see, so at the middle of interior span, here it is given at the middle of interior span. Now we are talking about interior span. So here interior span and here are the interior support. Now we are talking about the interior. So now this is the dead load coefficient. Dead load is written over here. So this coefficient is the dead load coefficient. This coefficient is live load coefficient. So for the middle, at the middle of interior span, your dead load coefficient is plus 1 by 16. Your live load coefficient is plus 1 by 12. And we need to multiply this coefficient by WL square. After that, at other interior supports. So at the interior supports, what is what is this coefficient? So at the interior support, the coefficient for dead load is, this is the coefficient for dead load, minus 1 by 12, and this is the coefficient for live load, minus 1 by 9. So dead load minus 1 by 12, for live load minus 1 by 9. So remember this coefficient. You don't need to remember, just see over here carefully, so that we are going to use that in our slide where the formula is given. These two are the coefficients, plus 1 by 16 and 1 by 12 for dead load and live load for middle of interior span. And for interior support, if you see, these two are the coefficients, these two are the coefficients for dead load and live load. Now again we will move to the PowerPoint presentation. So we go to the PowerPoint presentation again. So now again we came back to our PowerPoint presentation, and here now you can see this is at the middle of interior span. Just now we have seen that this is 1 by 16. This is the coefficient for dead load. Here is the coefficient, this is the, and next this is the coefficient for live load, which I have indicated in blue, 1 by 12. So now again if you put the value 1 by 16 as it is, 1 by 16 dead load, our dead load, here we have calculated the dead load, it is 5.81. So that value of dead load, L square span is 3 meter by 60, and again live load 4.5. So here the live load, it is 4.5 into L square by 12. So if you do this calculation, you will get the value, it is at 6.643 kilonewton meter. This is the value. Again, this is for middle of the interior span. Now at the interior support. So for the interior support, now again the same thing is there. For dead load, this is the coefficient. For dead load, the coefficient is minus 1 by 12, and for live load, the coefficient is again different. For the live load, this is the coefficient for live here, minus 1 by 9. Again, if you put the dead load value here 5.81, live load value 4.5, span is same for both, L square is 3, and coefficient 12 and 9. You will get the value of, this is the value 8.875 kilonewton meter. So we have calculated 4 bending moments totally. Bending moments, first we calculated the bending moment for end span. In second we calculate the bending moment for intermediate span. In end span, we have calculated the bending moment at 2 locations in end span. So those 2 locations are middle of the end span. So for the middle of the end span, these are the coefficients for dead load and live load, 1 by 12 and 1 by 10. And again, the second location is at the support, which is next to end support. At that location, we have again calculated the bending moment. So for that, again we have taken the dead load and live load coefficients, minus 1 by 10 and minus 1 by 9 is the dead load and live load coefficients over here. So again we have calculated the value of bending moment. All we are doing this by using the table number 12, page number 36. So again we have gone for intermediate support. In intermediate support, the span also, we have calculated the bending moment at 2 locations again. So first is at the middle. So at the middle we are always getting the sagging bending moment, positive bending moment. So the coefficients are 1 by 16 for dead load and 1 by 12 for live load. We just put the values, we got the bending moment. Again, we calculated at interior support, whatever may be the intermediate support, interior support. At that point, we have again calculated the bending moment, and the bending moment for dead load, the coefficient is minus 1 by 12, and for live load, it is 1 by 9. Okay. If I show you the diagram once again, where we exactly calculated the bending moment, I will draw the diagram over here. You see carefully. The space is very less. Still, I will try to draw the diagram with the precision. So here is the end support. These two are the end supports. Now I will not show each and every support. Just for your understanding, I will draw here 2 supports. Suppose this is your interior support 1, which is indicated by blue arrow. This is your interior support 2. Similarly, third support is there and fourth support is also there. So now here the points where we have calculated the bending moment is, see, first of all, at the middle of end span. At the middle of end span means this is this point. Okay. At the middle of end span means this point. Where is this profile is like this. This is your. So now if you put the value, you will get D required as a 59.37 mm, and then D provided is greater than D required. Hence it is safe. Whatever we have provided, it is more than what is required. Okay, so it is safe. Now once you take the check for depth, if this check is okay, this is satisfied, then you need to go for steel calculation. Okay, for the steel calculations, considering the maximum bending moment, AST is equal to. So here we are considering what we have written over here. We are going to consider the maximum bending moment, and we will provide the steel for maximum bending moment. Okay, so AST is equal to 0.5 FCK BD upon FY. This is the formula. 1 minus under root 1 minus 4.6 MU upon FCK BD square. So just you need to put the values over here. So the values are 0.5 is the constant as it is. For Fy is also constant. FCK is 20. Grade of concrete B is 1000. Width D is the effective depth. The small d is the effective depth. So our effective depth is 95. So we have put that value over here. Again we write the formula under root 4.6 mu. So now here you can see what is the value we have taken for mu. So for mu, we have taken the maximum bending moment. It is 9.729 into 10 raised to 6. So this is 9.729 is the maximum hogging bending moment. That is why we have given their negative sign if you see the previous slides. So this is the maximum hogging bending moment, and we are going to provide the steel for the maximum moment so that it will automatically get satisfied for all other bending moments. So here the value mu is nothing but bending moment which we got the maximum value. Okay, bending moment maximum. Here we have put that one. So now if you put all these values, you will get AST is equal to 303.96 mm square. This is the value of AST. Now after the AST, calculate the number of bars. So number of bars, how do we calculate the number of bars? So for the number of bars, the formula is area of single bar. Okay, area of single bar divided by AST. Okay, divided by AST. This is the value of AST, area of steel, divided by total area of steel. This is the formula. Okay, no, sorry. Uh, I think the reverse is true. So here area of single bar by total AST into 1000 gives you the spacing. Here you have the formula for this is a total area of steel provided, that is total AST divided by area of single bar, area of single bar. So if you do this, you will get the number of bars. So this is total AST divided by area of single bar. It works out to be 3.87. So we nearly round that figure because we can't provide the bars like 3.87 bars. So we have round up this to 4 bars. Now as the AST is 303.96 and number of bars is 3.87, but we have provided how many bars? We have provided 4 bars. So whatever we have provided, that we are now going to calculate. So AST provided, this is the required, and now what we have provided? So AST provided is equal to how many bars? 4 bars. So 4 into area of 1 bar. 1 bar is having diameter 10 mm. We have assumed initially the bar diameter as 10 mm. So it is pi by 4 into 10 square. This is the area of single bar. How many bars we are going to provide? 4 bars. So multiplied by 4. So this is what is the AST provided. 314.15 mm square. This is the AST provided. Now from the AST provided, we can calculate the percentage of steel provided. So for to calculate the percentage of steel provided, what is the formula? It is 100 AST, 100 into AST divided by BD. It is 100 AST divided by BD. So see over here, 100 constant as it is AST. So AST you have to give the AST provided. Okay, Here the AST is nothing but your AST provided. These bars are you are going to provide. So this value you need to put over here. Okay, 415.15. This is your AST provided. 100 AST upon BD. B is again 1000. D is 95. You already know this. So from that you will get the value as. From that you will get the value. It is 0.33. This is the value what we get. 0.33 is the percentage of steel provided. Okay, so now next point is the spacing of the bar. So we need to calculate this spacing. So for the spacing we have already seen on page number 46, clause number 26.3.3. Okay, so first of all we will calculate the spacing by normal method first. So the spacing is equal to what? Area of one bar divided by total AST multiplied by 1000. इथं जे मी आधी चुकून लिहिला होता ना फॉर्म्युला, इथं हा फॉर्म्युला सांगताना जो चुकून मी फॉर्म्युला लिहित होतो किंवा लिहिला होता, that formula is nothing but the formula for spacing. So here the formula for spacing is area of single bar. This is the area of one bar divided by AST provided. This is the total area of steel which we have provided. You always use the AST provided while calculating the spacing, multiplied by width. So what is the width? So width is 1000. That is why we have written over here 1000. हे 1000 म्हणजे नेहमी लक्षात ठेवा, this is multiplied by width असते नेहमी. Here you need to multiply by width. So our width, in our case the width is 1000. If you multiply by 1000 you will get 250 mm center to center. So your spacing, first value we got 250 mm center to center. Then we have already seen the spacing in the second case. So the spacing is 3D for the main steel. So 3D, D is nothing but effective depth of the slab. D is nothing but the effective depth of the slab. So what is the value then? 3 into 95. So it is 3 into 95. So it is 285 mm center to center. Okay. Now third thing, to calculate the spacing, it shall be taken as 300 mm. So from these three values, you need to choose the least value, least or minimum value for the spacing. So our first value is 250, second value is 285, and third value is 300. So from these three values, what is our minimum value? Minimum value is 250. So how many numbers of bars we are going to provide? We are going to provide 4 number of bars. What is the diameter of each bar? 10 mm. So here the concluding line is that provide 4 bars of 10 mm diameter about 250 mm center to center. Okay, and this is for per meter of slab. So this is for 1 meter width of the slab. Okay. So now next slide is, so after the main steel we are going to calculate the distribution steel. So for the distribution steel, IS code says that from clause number, for the distribution steel, on page number 48 the clause number is given. I have already written over here the clause number. So the distribution steel is 0.12% of gross area. Okay, so 0.12% of gross area. So if we go to the IS code now, if we see the clauses in the IS code, on page number 48 it is given. So we will move to page number 46, I think. We will see where it is exactly given. We will read that again so that it will also brush up you. The clause is given regarding the minimum reinforcement. What should be the percentage of minimum reinforcement we should provide, that is given in there. So on page number 48, page number 40, 49, 48, here. Now I will underline this. The mild steel reinforcement in either direction of the slab shall not be less than 0.15%, 0.15% of total cross-sectional area. For what? It is for mild steel. Okay. If the mild steel is there, then you should take 0.15%. However, this value can be reduced to 0.12%. Now the same value, so that this same value can be reduced to 0.12%. This is 0.12%. Okay, 0.12% for high strength deformed bars. Here they have mentioned high strength deformed bars. So high strength deformed bars means it is Fe415 or Fe500. These are the high strength deformed bars. For that, the percentage of steel given is 0.12%, and 0.12% of here you read carefully total cross sectional area. Total cross sectional area means whatever may be the total cross section is there, total depth. You need to consider the total depth over here, capital D. Okay, so now I will clear this and we will move to the spacing also. I think here on the same page, but you know the spacing now, you know the class. So we will move to the slide once again. So here now ASTD is equal to 0.12%. I have already shown you how to take that because in our problem Fe415 is given. So for Fe415 we have to take 0.12%. So 0.12 by 100 into B into D. So here you need to use the full depth. Okay, because they have told in the clause it is for gross cross sectional area. Okay, gross area or total area. Gross area means if this is your cross section, sorry, gross area means what? If this is your cross section, then this value, if this is the cross section, then this is B, and this total is overall depth. This total is overall depth, capital D, and your effective depth will be if you provide steel somewhere here. Suppose now the steel bars are provided at the bottom somewhere here. Here the steel bars are provided. Okay. So whatever may be the distance up to the center of this bar, center. This is your small d, that is the effective depth from top. This is your effective depth and this is your overall depth. Capital D is your overall depth, small d is your effective depth. Okay. So now here AST D provided, we have take the total area, total cross sectional area, that is B is 1000, D is, what is our total D? Total D is 115 and small d is 95. So it is 1, and what is the value of B? So B, all we have assumed 1000. It is 1000 into 115. So we got this value 138 mm square. So after that again calculate the number of bars. So again for number of bars, it is the total area of steel divided by area of one bar. For distribution, we have assumed 8 mm bar diameter. Okay, generally for distribution steel 8 mm, 10 mm is considered, but 8 mm it is okay because the area is less. So now here if you calculate the number of bars, then the number of bars are 2.74. So 2.74 means we round up that value to 3. So again we will calculate the distribution steel provided. The another name for distribution steel is minimum steel. It is also called as minimum steel. Okay. So in exam you remember this. Minimum steel, it may be asked for MCQ. Okay. So ASTD provided is equal to area of single bar pi by 4 into 8 square. Okay, this is the area of single bar multiplied by 3 because such 3 bars we are going to provide. So AST provided is this value 150.79. Okay, again we will go to calculate the spacing. Again we need to calculate the spacing of the bars. Okay, so again we need to calculate the spacing of the bars. Again the page number 46, the clause is given. Okay, so the spacing, what we will do first, by first method, what we are doing in spacing, take the area of single bar divided by ASTD provided, multiplied by what? Multiplied by width. It is always multiplied by width. So area of one bar divided by total AST multiplied by width, you will get the spacing, and this spacing works out to be 330 mm. We got the spacing 335.10, but always remember that while rounding up the spacing, you should always reduce the value, and while rounding up the depth, rounding up the number of bars, you should always increase the value. Okay, while rounding up the depth or rounding up the number of bars, you should always increase the value, but while rounding up the spacing, you should always decrease the value. As you decreases the value of spacing, the number of bars are increased, so it will be on safer side. Okay, if you increase the spacing between the two bars, then what will happen? The number of bars will decrease, and it will so it will reduce the strength of the slab ultimately. Okay, so now here 335.110, so we reduce the spacing, and the spacing works out to be 330 mm center to center. Second, by clause, the spacing must be for distribution steel, it is 5D, the value of D is 95, so 5 into 95, it is 475 is the answer. Last one is the 450. So we need to choose the least value from these three. We should take the minimum value. This is our value number 1, this is our value number 2, and this is our value number 3. Out of these three values, we need to take the minimum value. So minimum value is 330. So we can write the statement over here: provide provide 3 bars of 8 mm about 330 mm center to center. Okay, 330 mm center to center. So this is again for 4 meter width of the slab. This is again for 4 meter width of the slab. So this is what is the steel calculation we have provided. In the main direction we have provided 10 mm diameter bar, and in the distribution steel we have provided 8 mm bar diameter. Okay, you see these steps once again. I will give you half a minute, and you tell me up to this point, is anybody is having any difficulty, you tell me. I will give you 30 seconds. See all the things. We will move forward now. So next is the, here the check for deflection is taken. You need to take the check for several quantities: check for shear, check for deflection, check for development. Okay, so here the, in this slide, check for shear, then here the check for development length is also taken. In the previous one way slab design, if you see, the check for shear is taken earlier. First we check the slab for shear, and then we go for deflection. Here I have taken the check for deflection first. It doesn't matter whatever you are doing, you just need to follow the procedure, and you be sure that whatever you are providing the design, it is safe design, it is satisfying the checks. So now as we move forward now, see, check for deflection. Now check for deflection, percentage of steel provided is 0.33%. We have already calculated the percentage of steel, and it is 0.33%. Now again we should go for this page number 38, and we need to see that graph. Okay, and from that graph this modification factor is calculated. So here the formula Fs is equal to 0.58 Fy AST required divided by AST provided. So this formula comes from here, clause number 23.2.1, figure number 4, page number 38. Okay, so if we put the values over here in this formula, then Fs is equal to 0.58 into 415. 415 is the yield strength of steel. 415. Then AST required किती होता आपल्याला? What was the value of AST required? It is 303.96. If you see in the previous slides, it is 303.96. Now if you see over here, it is 303. I think somewhere here we have done the calculation. No? See, what is the required? This is our required value. So if you see that this is our required value, 303.96. And what we have provided? We have provided this one. We have provided 314.15. And what is our percentage of steel? This is the value for percentage of steel, 0.33. So 0.33, this is the provided value and this is the required value. Now again, if we move to the next slide, I will clear all these things first. Now in the next slide also, see here, percentage of steel provided 0.33 fs, we put the value here. AST required is 303.96 divided by AST provided 314.15. If you calculate, you will get the value as 332.89. This is the value, 332.89. This value you will get, and we can round up this value to the value which is shown on the line, that is 240. We have rounded up this value to 240. Now we will go to the IS code. We will see what will be the modification factor. What will be the modification factor for FS 240? Okay. So we will see the modification. Is my voice is audible? So now IS code. We will go to the IS code first. Page number 38. So in the IS code, page number 38. Where is the IS code? This is the IS code. In the IS code, page number 38. Where is the page number 38? So, this is the diagram. Now see here in this diagram. So what is our percentage of steel? Our percentage of steel is 0.33. Now if you see here, percentage of steel here, whatever given reinforcement, 0 0.4, 0.8, 0.2 means this middle value, it is nothing but 0.2. Okay. Here if 0.4 is there, then this middle value is 0.6. In this way this graph is given. Here 0 to 0.4 is there. So this middle value, it is nothing but it is 0.2. So this middle value, it is nothing but it is 0.6 for modification factor. Now we need to see for this line 240, FS 240. Okay, we need to see for this line. So here our percentage of steel is 0.33. So 0.2 and 0.4 या दोघांच्या मध्ये कुठेतरी in between here 0.33. Okay, and we need to project that. So if you project, now the line will not be that much of straight. So it will somewhere come over here. Here you can take at this point. Here we will take this point. This is randomly we have to take this point. And if we see the value over this side, so it will come somewhere here. So this value is somewhere above this line. Here somewhere the value is. Okay. So if this is 1.2 and this is 1.6, then the remaining will be, the value will be, just a minute. So now coming back to our point, if this is 1.422, then this value is 1.4 at this point. Okay, and it is just above this point. So I may take this value as modification factor as 1.45 or 1.5, both are correct, but 1.5 will be slightly more, so it is just passing 1.4 near about, so we can take 1.45. You can also take 1.4 also. Okay, it doesn't make much more difference. 0.05, it doesn't make much more difference. So here we will take the value 1.45. So now again we will go to the our slide to consider this calculation. So here, okay. So now again we will consider here the percentage of steel 0.33 if you put 240. So this value modification factor, this value here it is taken as 1.45. Okay. This value is taken as 1.45 as I have already told you. Now deflection. So to calculate deflection, d is equal to what? So end span divided by 23 into modification factor. Okay, end span, or you can take simply the span, whatever may be the maximum span, you consider this span over here. It is not necessary, it is always ends. Okay, so the span divided by 23 into modification factor is it is taken for the deflection. So now the value is 3000 is the span divided by 23 into modification factor is 1.45. So you will get the answer 89.95. How this 23 comes? This 23 comes from this. It is span to depth ratio is 20 for simply supported slab, and span to depth ratio is 26 for continuous slab. Okay, so we have taken the average of these two, 20 plus 26 divided by 2, it works out to be 23. So this value 23 we have considered over here to calculate the deflection. So now if you calculate the deflection, then it is 89.95 mm. This is the deflection. So D required for the deflection 89.95. So the deflection resist करायला जी depth लागणार आहे, that depth is nearly 90 mm. If I round up this, it is nearly 90 mm depth. And what depth we have provided? Our provided depth is, what is the value of provided depth? It is 95 mm. So it is economical also. We have provided this D, it is 95 mm, and required is 90, so it is safe. Hence the serviceability condition check is satisfied. Okay. So we have taken this check. I have also told you when there is need to take the check for deflection, and then when there is no need to take the check for deflection. Okay, here in this case also our PT assumed is less than PT provided, so you have to take the check for deflection. If your percentage of steel assumed is greater than your percentage of steel provided, then there is no need to check the deflection, it will get satisfied. The criteria will get satisfied. I will tell you here. If your percentage of steel, what you assume initially, okay, if this value is greater than your percentage of steel which you have provided here, 0.33 it is provided. If this value is greater, then if this value is greater, then there is no need to take the check for deflection. Okay, there is no need to take the check for deflection. You can directly write as the percentage of steel assumed is greater than the percentage of steel provided, therefore the deflection criteria is satisfied. Okay, and if the reverse case is there now, if the reverse thing is there, if your percentage of steel which you have assumed is less than your percentage of steel whatever you have provided, in this case now our percentage of steel assumed is 0.3 and what we have provided it is 0.33, then you need to take the check for deflection. You cannot write directly that the deflection criteria is satisfied, then you have to take the check for deflection. Okay, so here we have taken the check for deflection. So now after this we will move to the next check, and next is the check for shear. Okay, so next is the check for shear. So in this also maximum shear force occurs at the next to the end support. So the maximum shear force is calculated. Okay. So now here I have shown the diagram where is the maximum shear force uh, we need to calculate occurred. So this is the point where the maximum shear force is occurred. The support next to the end support. Whatever your support which is next to the end support. So this is your end support. This support is the end support, and next to end support is this support. So at this point your shear force will be maximum. Here also this is your end support, next to this support is your shear force, you will get the maximum value over here. Okay, and for that we need to calculate the see the coefficient again. So we will again move to the IS code and see the coefficient. Okay, so now we have to go for table number 13 in the IS code. Now in the IS code table number 13. So again if you come to the IS code table number 13, this is table number what? 14. So about this point. Here somewhere your table number 13 is there. Uh, this is your table number 13. Now earlier to calculate the bending moment we have used table number 12. Okay, we have already used this table to calculate the bending moment. Hmm. Now we have for shear coefficient. Now for the shear we need to use the table number 13. So again same thing is there. Dead load. This is dead load. Here it is live load. Okay, and here they have said that for obtaining the shear force the coefficient shall be multiplied by design load. So our design load is nothing but our design load is W into L. W into L is nothing but the design load. Okay, W into L is design load, and the movement bending moment is nothing but it is W into L square. Okay. So now uh, for the design load at the end support. So the coefficient at the end support is zero point 0.4 for dead load, 0.45 for live. Okay. So the coefficient at support next to the end support. Support next to the end support. The coefficient is for dead load it is zero point 0.6, for live load it is zero point 0.6. Here outer side and inner side. It doesn't matter. You don't consider inner side. Okay, you should not take these values in examination. You always go for the outer side because these coefficients are on higher side. If you design out on higher side there are less chances for the failure of the structure, and if you compare these values, here it is zero point 0.6, here it is also zero point 0.6, so there is no difference. Here it is zero point 0.6, here it is 0.55, so 0.05 the difference is there, so it does not create much more difference in the shear force. Okay, so you will always go for the outer side whenever you are considering the at support next to the end support. So shear force at support next to the end support. So these are the coefficient. So I will write this is the coefficient for dead load. This is the coefficient for dead load. It is live load, live load. Similarly here also this is the coefficient for dead load. This coefficient is for live load, and all other interior supports 0.5, 0.6. Okay, but what the actual procedure says now, you take each and every coefficient and you calculate the shear force at each and every point, and out of that you consider the maximum shear force for the calculation. This is what is the procedure, conventional procedure. Okay, but I will tell you one shortcut to calculate the maximum shear force. Now we want SF maximum, shear force maximum, ह्यालाच आपण VU म्हणतो, VU notation देतो आपण. So VU, how to take this max. Now I will share my screen to you. uh, I think we are discussing on the IS code, no? So here now if you see that the coefficient at the end support, I will draw here diagram first so that you will understand what is our case and what we are talking about. So this is our continuous slab. Okay, here is the end support. This is also end support. I have indicated end support by red color. Now I will take blue color for intermediate support. So for intermediate support, this is 1, 2, 3, and 4. I think these 4 interior supports we are having. Okay. So and these are our span. This span is this portion. This span we called it as the end span. This is also our end span, and these are the intermediate spans. So now what they are saying that uh, what they are saying now at the end supports. So this is the dead load coefficient and this is the live load coefficient. Okay. So I will write here dead load. At the top I will write dead load coefficient, at bottom I will write live load coefficient. I will again choose the different colors so you can distinguish. So for dead load at the end support, at the end support means this point. This is at the end support. So at the end support for dead load, what is coefficient? For dead load the coefficient is 0.4. And what is the coefficient for live load? The live load the coefficient is 0.45. So for the live load, the coefficient I will write here 0.45. 0.45 at this point, same point. This is the coefficient for dead load. This is the coefficient for live load. Next, what they have said, add this support next to the end support. Now this is our end support. Next to end support is this one. Okay, here also. Whatever value I am writing here for this end support, same value is applied for this end support. Here I am not having the space, that is why I am not repeating this value over here. Okay. So now this is all end support, this is also your end support. नाहीतर म्हणणार इकडं लिहिलं नाही. हा पण तुमचा end supportच आहे आणि हा पण end supportच आहे. इकडे जे काही कोएफिशियंट असणार आहेत तेच कोएफिशियंट या end supportला असणार आहेत. इथं मला स्पेस नाहीये म्हणून मी लिहित नाहीये. Okay. So next is the add support next to the end support. So add support next to the end support means this point here. This is the point. Okay. So add support next to the end support, the dead load coefficient. So this is your dead load coefficient, this is your live load coefficient. So dead load coefficient is 0.6 at this point. Okay. And what is the live load coefficient? Live load coefficient is also 0.6. So here I will write again 0.6, 0.6. This is for live load. Same is apply for this support. This is also intermediate support. Okay, so these two are the intermediate. I will give the at least naming. One end support first point. I will call this as a 1. म्हणजे काय जे इकडे असेल ते इकडे सगळं रिपीट आहे. Here it is. Intermediate support. I will call this as 2. So this is also your intermediate support. 2. काय जे इकडे असेल ते इकडे as it is repeat. And this is your 3. These are the interior supports. Intermediate interior supports. So at this point, what are the coefficients? So the coefficient for dead load. So now again see here, this is your dead load coefficient, here it is the live load coefficient at all interior supports. So dead load coefficient is 0.5. So I will write here 0.5 is the dead load coefficient. And what is your live load coefficient? Live load coefficient is 0.6. So again I will write here 0.6. Okay. Now what is the actual standard procedure now if you want to calculate the shear force? The procedure says that what you needs to do now if you want to calculate say shear force at this point, if I want to calculate the shear force at this point, then what should I do? uh, I should take this coefficient into the account and multiply that by design load. So first coefficient is of dead load, so I will write here VU is equal to, this is our 0.1, so VU1 maybe, so it is 0.4. 0.4 is the coefficient for what? Dead load. So I will write here W into D, whatever may be my dead load, into L. L is the span. Okay. Plus here again for live load the coefficient is 0.45. So I will write in the next bracket 0.45 into WL live load into L. Okay, and in this way if you put the value of dead load and span, live load and span here, you will get the value of shear force. So that shear force is correspond to this point because we are using the coefficients from this point. Okay. Similarly, you need to calculate the shear force at this point also and shear force at this point also. 1, 2, and 3. And out of these three, whatever may be the maximum shear force that you should take for the design. That you should take for the design. Now, there is one shortcut way to calculate the maximum shear force. You just see the coefficient. हे बघा मला W इंटू एल नी तर सगळीकडे मल्टिप्लाय करायचंच आहे म्हणजे एकदा डब्ल्यू डी डेड लोड इंटू एल नी मल्टिप्लाय होणार आहे एकदा लाईव्ह लोड इंटू एल नी मल्टिप्लाय होणार आहे बरोबर आहे डेड लोड अँड लाईव्ह लोड इज नॉट गोइंग टू चेंज dead load and live load the values are same this span is also not going to change then the value of shear force is depending upon what it is depending upon the coefficients only because the span is constant throughout 3 meter this value already we have calculated this value also we have already calculated live load and dead load so these values are not going to change so changing value is only the coefficient now if we want to calculate the maximum shear force then we will see the maximum coefficient to calculate the maximum shear force we should search for maximum coefficient now search over here at which point you are getting the maximum coefficient now if you observe that at this second point here at this juncture you are getting the maximum coefficient coefficient for dead load is zero point 0.6 and your coefficient for live load is also zero point 0.6 so both are maximum value are you getting me if you go for this 0.45 zero point 0.6 is greater than 0.45 0.4 zero point 0.6 is greater than 0.4 0.5 zero point 0.6 is greater again here it is 0.6 zero point 0.6 equal so at this point you will get the maximum shear force now from this I can conclude and I can write over here that if I want to calculate the VU max maximum shear force then I should take 0.6 into dead load into L okay and coefficient for live load is also zero point 0.6 plus 0.6 into live load into L also. Okay so this I should use 0.6 0.6 is the coefficient I hope you are clear with this whatever explanation I have given right now now we will move to our slide and let us check what the coefficients we have considered so these coefficients finally we have taken to calculate the maximum shear force 0.6 0.6 dead load live so let's move back to our slide let's so in the slide here I will open this now see here what is given here they told us the maximum shear force is Bu is equal to zero point 0.6 into WL that is Bu is equal to zero point 0.6 into WD plus WL into L okay I have already told you maximum shear force will exist over here at the support which is next to end support these are your end support this is the sample diagram which I have shown in the IS code right now it is our actual diagram so now VU is equal to zero point 0.6 as it is dead load live load into L I have just multiplied this L over here if you multiply this L inside then it will be WD into L and WL into L and the coefficient is zero point 0.6 for this and zero point 0.6 for this also okay. So just if you put the values then V is equal to zero point 0.6 dead load is 5.81 live load is 4.5 multiplied by span is 3 you will get the maximum shear force so this is the value of maximum shear force okay. You will get this value, maximum shear force. So now from the maximum shear force you know that we need to calculate the nominal shear stress tau v the shear stress which is actually present in the slab that we need to calculate so that shear stress is called as a nominal shear stress tau v so again basic formula is used over here we know that stress is equal to what stress is equal to load divided by area that formula is used over here so here the stress tau v is equal to vu is the load means shear force divided by area is b into d So if you put the value, this is the shear force, it is in kilonewton, so multiplied by 10 raised to 3. Then area B into D, B is 1000, D is 95. Okay, so if you calculate this, you will get this value, 0.2 Newton per mm square. This is your nominal shear stress. Okay, so now after the calculation of nominal shear stress, so normally the shear force is always at the support. Okay. The maximum value of shear force is always at the support. It is not always maximum at the center. Shear force is always maximum at the support. And now in our case, we got the maximum value of shear force at the point where at the support which is next to end support. Okay, at that point we have got this value of maximum shear force. So the percentage of steel at support. What is the percentage of steel at support? It is 0.329, which is we have actually considered this as a 0.33. 0.33. कळतं ना? इतर डिवायडेड बाय 2 करून घ्यायचं नाही पर्सेंटेज ऑफ स्टील. का घ्यायचं नाही? कारण की we have already calculated what is the bending moment at the support and what is the percentage of steel at the support. Okay, if you imagine that this is our case, this is your end support. What was our bending moment diagram? Our bending moment diagram will be like this: at center sagging, then here it is hogging, then again it goes for the sagging, then again it goes for the hogging, then again sagging, and it continues. Okay, again sagging, then hogging, again sagging. So what we have done now, this shear force is maximum at the support. Where is the maximum value of shear force now? The maximum value of shear force now existing at this point here. Here at this point your shear force is maximum. So now what is the percentage of steel over here? So here we have already calculated the bending moment. That value of bending moment is 9 point or 8 point something. That was our maximum bending moment we have calculated at this point. So already we know what is the bending moment at this point. We have already calculated the bending moment at this point. So from that bending moment, we can easily calculate the percentage of steel. So from that bending moment, the percentage of steel is calculated. So here I have written the percentage of steel 0.329, that is 0.33 from the bending moment which we have previously calculated. So I will show you that bending moment if you are having any confusion. That bending moment is bending moment and percentage of steel. See here, bending moment and percentage of steel. I think previous slide. This bending moment minus 9.729. This is the bending moment at support next to the end support, and this is the maximum value of bending moment, and it is existing at the support. Okay, so this is the maximum value. Just 1 minute. Huh? Hello. बर 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 ठीक आहे मी घेतो त्यांच्याकडे. Okay, so now here the movement by maximum value we have calculated as 9.729. So here the percentage of steel for that moment is 0.33%. That also we have calculated. Here the maximum value is 9.7. At this point, at this juncture, the maximum bending moment value is 9.7. Okay, so as I have already written out. So the shear strength of concrete is equal to tau c dash. Shear strength of concrete, it is 0.39. It is calculated from page number 73. So it is calculated for the percentage of steel, which is 0.33. I will clear all these things and we will move to page number 73 in the IS code. So in IS code, page number 73. page number 73. On the page number 73, that table is given to calculate the tau c. Okay. I think it is table. We used this table in previous problem also. So here is the table. Table number 19. So the table number 19, and here you know that 100 AST upon ED, so it is the percentage of steel. So in our case, our percentage of steel is 0.33%. Percentage of steel is 0.33. So our 0.33 value comes between these two values. Here somewhere 0.25 and 0.50 च्या मध्ये येईल कुठेतरी. Here somewhere you will get the value of 0.33. So our grade of concrete is M20. So what are the values? So these two are the values in between which we need to do the interpolation. So we must do the interpolation in between these two values, and we should get the value for 0.33. Already all of you are knowing that how to do the interpolation. In design of steel structure, many of times you might have done this. Okay. So for 0.25 it is 0.36, 0.50 it is 0.48. So you need to calculate what is its value for 0.33 from this table. So after this, now after you are getting this value, we will switch to our PowerPoint presentation. Here now, see, shear strength of concrete. After you interpolation, you will get this value, 0.39. Okay, after the interpolation, you will get this value. It is from clause number 40.1, page number 73. Now, permissible shear stress tau c is equal to k into tau c dash, and we have already seen in the last example also. I have shown you that this value of k, is 1.3 for solid slab. Okay, which is having depth less than 150 mm. So for this lesser depth, we should take the value of k is 1.3 and tau c dash value is this value. This is the value of tau c dash. Okay, and this also given on page number 72. Now if we go to the page number 72 again, in the IS code, so page number 72. So we will see the page number 72. There is a small table. See, this is the table. So now in this table, if you see, overall depth of the slab is given over here and the value of k is there. So here what they have said, if the depth is 150 or less, this is the important. If the depth is 150 or less, what is the value of k? The value of k is works out to be 1.50. This is the value of k from this clause. So that value is used in our further calculation. So if I see here, the tau c is equal to, that is permissible shear stress is equal to, this is our nominal shear stress. What is tau v? Tau v is nominal shear stress. This shear stress is right now developed in that slab. Okay, and this is the permissible shear stress. So up to this value we can allow the shear stress. Beyond this value your slab will fail. So permissible shear stress tau c is k into tau c dash. If you do the multiplication, you will get the answer. Tau c is equal to 0.51 Newton per mm square. 0.51 0.51 Newton per mm square. So here your nominal stress tau v is less than tau c, hence it is safe in shear. Okay, म्हणजे जनरेट किती व्हायला लागला आहे बघा इथं नीट व्हॅल्यू बघा. What is generated? Nominal shear stress it is here. So generate व्हायला लागला आहे 0.20. So developing the shear stress which is developed, it is 0.20, and how much permitted? So how much allowable? Allowable is 0.51. म्हणजे आपण 0.51 पर्यंत त्याला अलाउड करू शकतो तेवढा shear stress, आणि तिथं ऍक्च्युअली shear stress येतोय किती तर 0.20. So it is safe. This is what is the meaning. So here the tau v is less than tau c, hence this slab is safe in shear. Hence this slab is safe in shear. Now we will move to the last check, that is this check for development length. So for this check, I have already told you the formula in the last lecture itself, and that same formula we are going to apply over here to calculate the development length. Okay, so I will first of all clear all this. The formula, this formula which I already told you, 1.3 m1 upon vu plus l0, this is given in the IS code, clause number 26.2.3.3, page number 44. This we have already seen, and this is the formula for development length. LD is equal to phi sigma s upon 4 tau bd. This also I have explained you in the detail in the last lecture itself. So the clause number 26.2.1, page number 42, it is given on page number 44. So I will move to the previous slide. So here see M1. M1 is always calculated as mu by 2. This is the formula for M1. So our mu value 9.729. This is our maximum hogging moment, which is at the support next to the end support. Divided by 2. This is the value of your M1. Then Vu. Vu is the value of shear force. Okay. So this shear force value is 18.58. But don't take this shear force value in the calculation of development length. In the calculation of development length, don't take this value. Development length म्हणजे काय असणार आहे? Development length is always at the end. If I draw the structure like this, okay. असा जर तुमचा स्लॅब असेल समजा, मध्ये एक सपोर्ट काढतो अजून असा, हा कंटिन्यू आहे पुढे स्लॅब. Okay. The development length means what? When a bar comes, suppose now if I show you the bar, the development, suppose the bar starts from here right this point, it will come to this point and it will move down. Okay, as soon as it will start moving down beyond this level, whatever I am showing here in dotted line, beyond this level. So after this level, whatever is the length of the bar up to the in the beam, or you can say in the support, that length we called it as a development LD. Okay, and at this here at this juncture, if this is the intermediate support, this is the intermediate support, and this is the end support. In intermediate support, there is no bar going into the support. Okay, in the interior support, we does not bend any bar. Slide is not visible. Okay, I will stop share and once again I will start share. Now is it visible? Slide is visible now. Let me know. Yes or no? No? Are you getting my voice? Still the slides are not visible. Voice is getting but slides are not visible. Okay. I will check once again. Just a minute. Now it is visible. Still it is not visible. we will do one thing, disconnect and rejoin. Okay, now the slides are visible. Are you able to see the slides? Okay, now it is visible. Yes, so we will move forward now. Uh, so here now at this point, this is the development length which we are seeing right now. So m1 is equal to mu by 2. This is the value. Now vu is equal to what? 18.558 kilonewton at next to the end support. This value is given. Okay, but development length is always calculated at the end support. You remember this. So development length is always there at end support. It is not at any intermediate support. Development length is always at the end support. Okay, so we need to calculate what is the shear force at end support. To calculate this value of vu, we need to calculate what is the shear force at end support. So are you getting this point or not? I will just show you here with the drawing. So now this is suppose now slab. Okay. Here it is end support. I will draw some inclined line as there is a lack of space. This is the intermediate support, and again here it is the end support. Okay. This is the section. Now if I show you the bar in the slab. Now suppose one bar is come from this side here up to this point, and then it moves like this inside. Okay. As soon as it cross this bar cross this level, okay, this level, it starts entering into the support. This is your slab. This top is your slab, and this bottom is your support. This is your support. As soon as this bar starts entering forward from this point, whatever may be the length it travel into the support, that length, this length is nothing but our development length generally. Okay, it is a development length. So now here what is happening, and the similar thing is with this support also, because this is end support, this is end support, and this is also end support, this is also end support. So similarly a bar may can go in this way. This is the profile of the bar. Okay, but no bar will bend at this move in the intermediate support. This is your intermediate support. This is an intermediate support. Suppose any other bar continues from this point here. It may go up and continue like this, or it may continue like this only in a straight line. Or some bar may come from this side in this way, another bar from this side it will bend in this way. This way the bar distribution is there. So in the intermediate support, no bar will merge or embedded. So there is no development length at the intermediate support. Okay, there is no development length at intermediate support. So development length is only present at which support? End support. So therefore we need to calculate what is the shear force at this end support. So now to further simplify this, I will tell you again. Now up till now what we have done, we are having this our large span. I will show first intermediate support 1, 2, 3 and 4 intermediate supports, and I will show the end support by red color, end support. So we have calculated our maximum shear force at this point. If you remember VU max, and its value is 18.5 something at this point, means at this point. At this point we have calculated our maximum value of shear force. But development length is not there at this point. development length always exists at the end point here. Your development length is always exist at the L point. I will write shortly LD. LD. So your development length is always at the end point. So for the development length calculation, you need to calculate what is the shear force present at this point. What is the shear force present at this point? So we have already seen in table number 13 dead load and live load coefficient for the shear force at this point. And if I am not wrong, then the dead load coefficient may be something around about zero point 0.4 and live load coefficient was 0.45, I think, something in this range. We will see right now. Here also, no, both are zero point 0.4. Okay, both are zero point 0.4. So this is not there. Maybe. Here it is, both are taken as 0.4. So I will not go to the I score now. So we know this already. So the shear force. Now I hope you understand that why we are not taking this value. Okay. So V is equal to 18.55 kilonewton at the next to the end support. This is important. Shear force at end support we need to calculate. So shear force at end support, this is the coefficient for dead load as well as live load, 0.4, zero point 0.4. Dead load, live load, we already know the values, 5.81 and 4 point something. So we got this value shear force. 12.37 kilonewton is the shear. Okay. Now we calculate the value of M1, we calculate the value of Vu. Now we need to calculate the value of L0. So for L0, we discussed in the last lecture itself the formula. L0 is equal to width of support divided by 2 minus clear cover. So width of support. So here the width of support is not given in the problem also, and we have also not assumed the width of support. If we have assumed, we will take that value. If we have not assumed, we will assume width of support here only. So the width of support which is assumed value, it is taken as 150. In the last problem we have assumed width of support as 120. Now here the value is taken as 150. So this value is 150 width of support. This is assumed value divided by 2 minus clear cover. Clear cover for slab we assume it as a 15 mm. So if you do this calculation, 150 by 2 is 75. 75 minus 15, it is 60. So this is the value of L0. So now we move to the next slide. So now just to plug in all the values in the formula, just plug in all the values. So what do we get if you put all the values? 1.3 m1 upon vu plus L0, 1.3 m1 is 4.86. Convert this value into Newton mm. Okay, divided by vu. Vu is the shear force which we have calculated, and plus 60. Okay, plus 60. So we will get this value, 571.17 mm. Then calculate the development length, 5 sigma s upon 4 tau bd. For sigma s is 0.87 into fy. Again sigma s. So sigma s is equal to 0.87 into fy. Then phi is the bar diameter, which is 10 mm. Then 4 into tau bd. 4 into tau bd. The value of tau bd is 1.2. But for M20, but multiply this value of 1.2 by 1.6 for 60% increase. Okay, when the bars are at the tension side, 60% we need to increase this value. This we have also discussed, and this is also given on page number 43. And after this, if you solve this, you will get the LD development length as 470.11 mm. Now compare the value. LD is 470.11 is less than this value, whatever we have calculated here. So it is safe. Whenever the value of LD is less, then it is safe. If the value of LD is more, then you need to revise the section. So it is safe. So here the third check is also over. Now the reinforcement details which are provided over here. So we have provided our main steel bar. Main steel bar is what, 10 mm above 250 mm center to center, and the distribution steel, this dot which you have seen over here, this is your distribution steel. It is 8 mm 330 mm center to center. Now see the main steel bar. First bar will start at this point. It will bend like this, and it will move over here. Okay, it will move over. and it will continue. So this is the profile of the first bar. The second bar, now see here. This support is the intermediate support. This is the next to the end support. This support also. This is the intermediate support, and this diagram is continued. This is your end support. So now here, if you see for that intermediate support, a bar starts from this point. It is continued up to this point. Then it is bent, and this will go in this side up to this point, up to the center of this support, a little further. Next main steel bar will start at this point. It is bending profile is straight line, then it will bend, and then it will move up to this point here only. Okay, it will move up to this point. I will, if I show you the bar, see, this bar will start at this point here like this, then it will bend here, and it will move further up to this point, somewhat distance, some distance after the center. And in the case of this bar, here it is, I will show by different line. This bar is start profile, it will start at this point, then it will get bent, and it will move towards this side. So this is your end support, and this is your support which is next to end support, and the distances are given over here, 750, that is L by 4 from the center of the support. This is the distance, L by 4 from the center of the support. Okay, and the bar from which is started from this side and bend at this point. So this distance from this center, हे distance या center पासूनचं, this must be 600, that is L by 5 in the case. Here it is 600, but L by 5. You remember this standard, L by 5, where L is the span. हे कसं 600 आलं L by 5, तर L तुमचं 3 मीटर आहे सेंटर स्पॅन. So 3000, 3 meter means 3000 mm. 3000 divided by 5, you will get 600. Here 3000 divided by 4, you will get 750. And this same profile, now you see this same profile, whatever I have shown over here, this same profile gets repeated here at the next support. This same profile gets repeated at the next support, and this is the profile at end support. End support, it will look like this. Okay, I will show you this bar also. This bar will start from this point, main steel, it will bend. Okay, but this distance is L by 7, so 3000 divided by 7, it is 425. So, and then this bar is bent and move forward up to this point. Okay, and the same is the mirror diagram is over here, top of this. And whatever the dots you are seeing here, these dots are nothing but your distribution steel, in another direction towards the width, parallel to that line. Okay, parallel to the width, and this is along the length. This is the steel which is parallel to the length that I have shown over here. So with this, our one-way continuous slab ends over here. So up till now we have studied the one-way slab and one-way continuous slab. So in the next lecture we will solve one more example of one-way slab, and then we will go for two-way slab. Okay. So right now we will stop over here.